Hey there, here we go into something that is not on the BC exam, just putting it out there, and sometimes it's left out of calculus classes in general, but I cover it all. And so here we go with arc length and surface area involving polar curves. So let's start out with arc length. So first, I just give you the function. We're gonna go over why that function is the way that it is in a second. But to find arc length, you need this function. It's the integral from alpha to beta that's over the angle measures that trace out whatever arc we're finding. Make sure that you don't trace the arc out more than once, because in polar curves, if you go beyond 0 to 2 pi, you're often, not always, but often going to end up looping more than once, and that would be doubling or tripling an arc length. So make sure that you only find the arc length once. Anyway, find the arc length of r equals 8 plus 8 cosine theta, that's this thing right here, over 0 to 2 pi. So that's essentially the circumference of the whole thing, all the way around. All we do is follow that formula. So we need r prime of theta, or dr d theta, according to that formula. So dr d theta is equal to, well, the derivative of 8 is 0. The derivative of this will be minus 8 sine theta. All right, so let's see what this gives us. So we're going to have the integral from 0 to 2 pi. And knowing our 8 plus 8 cosine theta is a cardioid, it takes from 0 to 2 pi to trace it out once. So we're not doubling up here, which is good. And we end up with the square root of, let's see. Well, we get the square root of, and here's an interesting thing. You've got to be differentiable on the entire curve. Like dr d theta has got to have values. It can equal 0, but it's got to be differentiable the whole time, which this is. So we should be in good shape there. Now, what we have here is we could use symmetry. We could also go from 0 to pi and double it. We could do that, or we can just go this way. So this is going to be r squared, which is 8 plus 8 cosine theta squared. And you are allowed to use a calculator here. Plus, and that's going to be negative 8 sine of theta squared. All right, so that right there is our formula, just plugging it in exactly as is. What we're going to do from here, oh, you know what we're going to do. We're going to integrate this thing with our calculator. So I'll be right back with the decimal answer, but that's it. That's your setup. And I kid you not, we got a nice answer of 64. Might have been able to do that one by hand, maybe, would have involved some trickeration, but either way, we get to our answer, and it is exactly 64. It's all about the setup. That's it for arc length. I'm not going to go over more than one example. It's pretty simple, pretty straightforward. But the question becomes, where does this formula come from? Well, so where the formula comes from is the idea that we can parameterize really any polar curve. That's how we've been dealing with them, right? So we know that arc length is the integral in parametric form from a to b of the square root of dx dt squared plus dy dt squared. And we've gone over the y before over that. And if you got questions on that, go back to chapter 10, check out the y. I'm sorry, chapter 11. That's early chapter 11. That's where we're doing arc length there. So check that out earlier in this chapter. And you'll be able to see, oh, okay, I see why that is. So it's the same thing as if it's in terms of theta or t. That doesn't matter. So I'm going to now substitute in the idea that dx d theta squared and dy d theta squared come from this, right? So dx d theta, this is the way that we parameterize a polar curve. We take any function r, any polar function r, and we multiply by cosine theta to get x, multiply by sine theta to get y. Now if I take the derivative of x, that's first times the derivative of the second is minus sine theta, I'll stick the minus out there, plus the second times the derivative of the first, which is dr d theta. Okay, all right. dy d theta is equal to, first d second is r cosine theta, plus second d first, sine theta, dr d theta. Now when we plug all of this into here, what that means is we're going to get the integral from some starting angle to some finishing angle, a to b, again, making sure not to trace it out more than once. And don't worry, it's not on the BC exam. I'm just kind of mentioning that down here. And we're going to square everything out and see what we get. We could get a really, really long radical sign. I don't even know how long. When I square this out, I'm plugging this in, this part into here, and I'm squaring it out. So that's minus r sine theta plus cosine dr d theta squared. So this gets squared. You get r squared sine squared theta. We're going to get this times that and then double it. So that's going to be a minus 2r dr d theta. Interesting. Sine theta cosine theta. Ugh. That again happens when I square this entire thing. These get multiplied by each other when you FOIL it, and then doubled. And then I'm going to add on to that this squared, which is cosine squared theta dr d theta squared. Gross. I know, right? I could have just kept all of that squared. But let's keep going from there. Now we're going to add on the square of that. It's going to be very, very similar. You'll get r squared cosine squared theta. Interesting. And then you're going to get 2 r dr d theta times cosine theta sine theta. Barely going to fit this thing in there, if at all. Yep, we're not going to fit it in. Then from there, we're going to be adding on to that the square of sine theta squared dr d theta squared. Oh my, that's gross. But it gets really nice really fast. This and that are the same thing. 2r dr d theta cosine theta sine theta cancel. The other thing to notice is I've got an r squared sine squared and an r squared cosine squared. So that's going to be the integral from a to b. Oh, this is nasty. Of r squared times sine squared plus cosine squared. That's nice. It's really nice because that's going to equal 1. Plus, check this out, you've got a dr d theta squared that can be factored out of each of these. So dr d theta squared times cosine squared plus sine squared. Do you have to know how to do any of this? No, I just want to show you where the formula came from. It's pretty gnarly. And that is times d theta. Well, each of these is equal to 1, so you end up with the integral from a to b of the square root of r squared times 1, it's just r squared, plus dr d theta squared times 1 is dr d theta squared. All right, and there's your formula. I wanted to show you where it came from. That's the arc length formula. On the next part of this video, which is coming up right now, we're going to go to surface area. All right, now this one is really barely ever taught, truly. But if it is, I got you covered. So what I did here is I essentially just linked between what we know as parametric arc length and surface area coming from that, and then blended it into polar. So from before, and if you need a review of it, check it out and the why behind it earlier in chapter 11, where we go over parametric equations and surface area. So if we're revolving about the x-axis, we had 2 pi a to b of y of t times the arc length. Now we would have r sine theta, which is y, times the arc length, but in terms of polar. If we're revolving about the y-axis, well, that would be the x of t times root x prime of t squared plus y prime of t squared, arc length, the 2 pi. Now, if we're in polar, x is r cosine theta, and here's the arc length function. So please, don't memorize this without first understanding these two earlier in this chapter 11, and then you'll know those. So let's set one up and do one, but it's just about using a formula that's nasty looking, but it does come from parametric equations, as so much of this chapter has with polar equations. Find the area of the surface formed by revolving the following region about the given axis of rotation. So we got 2 cosine theta from 0 to pi over 2. All right, so 2 cosine theta we know symmetric about the x-axis, and just from 0 to pi over 2 would be that right there. If we're going to revolve it about the x-axis like so, then what we notice is the radius is going to be right there. It's going to be our r value. So if we take a look at it, overall, the best way to remember surface area is 2 pi integrated from a to b of r ds. That's it. And if we know it that way, we can use our polar functions to figure that out. So that's 2 pi from 0 to pi over 2. R, this thing right here, well, in this case, that is going to be, now be very, very careful. You might be tempted to be like, oh, it's r. R is that distance there. I shouldn't use that to confuse you with this. That's not r of theta, that's your radius. All right, so that would be your radius. In this case, that's a y value. So I'll just say y times ds. So the radius equals y, not the r function of theta. And so y is equal to r sine of theta times the arc length, which we now know is r squared, or 2 cosine squared d theta. Sorry, just 2 cosine squared theta. So it's r squared plus dr d theta squared. Okay, so dr d theta, we'll find right here, I'll just throw that down, is equal to minus 2 sine theta. And this one we actually might be able to do by hand if you really wanted to. And so let's do it. So this is going to be equal to minus 2 sine theta squared d theta. Now how can we do this one by hand? Let me show you. So this is 2 pi times the integral from 0 to pi over 2. R is 2 cosine theta sine theta. And the inside's actually going to get really nice. You might be like, what? How? This is equal to, as we square it all, 4 cosine squared theta plus 4 sine squared theta. That's all inside the radical right there. This we could factor out of 4. That's 4 times cosine squared plus sine squared. That's just 1. All of this is just 4 inside the radical. It's quite a big square root. So this becomes 2. That is 2. 2 times 2 is 4, which I'll take out, times that 2 is 8. That's the integral from 0 to pi over 2 of cosine theta sine theta. Now you could use u substitution here if you like. Let's let u equal to sine because the derivative is cosine. It's perfect. Watch this. du is equal to, it's been a while since you've done u sub, I bet. So if you need a review on that, check out chapter 4. Oh my. Cosine theta d theta is the derivative. So this part right here is du. We got 8 pi times the integral when, let's see, x or theta equals 0, u equals 0. Just plugging it in here. When theta equals pi over 2, u is sine of pi over 2, which is 1. Oh, that's really nice. And what we end up with here is cosine theta d theta is du, sine theta is u. Oh man, what an easy integral. So that, not really. I mean, it involves a lot of manipulation. That's 8 pi times u squared over 2, evaluated from 0 to 1. And when we plug that in, well, 0 is going to give us 0. 1 squared is 1. Half times 8 is 4. It's 4 pi. Done. And you might be like, wait, what? Well, if you think about it, geometrically, this ends up being a sphere, and the surface area of a sphere is 4 pi r squared. The radius of this is 1. 4 pi r squared. 4 pi times 1 squared. 4 pi. Or you could use a calculus to back it up. All right, I'll leave it at that. Listen, arc length at surface area, I'm not going to say it's useless, but it very infrequently comes up. I made these videos, though, just in case you needed it to be covered, and the why behind each of those is pretty gnarly. See in the practice exercises, we've got a lot of practice there, especially with area. Peace.